At the dawn of the 20th century, the atom seemed almost solved. Scientists knew that matter was built from tiny units, each carrying a positive core surrounded by negative electrons. The positive charge came from particles called protons, and for a while the arithmetic looked simple. Count the protons, and you would know both the charge and the weight of any atom. But nature refused to cooperate. When physicists weighed atoms carefully, the numbers broke apart in their hands. Take helium. Its electric charge matched exactly 2 protons. Yet helium weighed as much as 4 protons. 2 units of mass had vanished into the equation with no explanation. This was not a rounding error or a flaw in the instruments. The same discrepancy appeared everywhere. Carbon carried 6 units of charge but 12 units of mass. Oxygen showed 8 charges and 16 weights. Again and again, the mass ran roughly double the charge, as though half the material inside the nucleus had gone silent, contributing weight but announcing nothing. Something heavy was hiding in the heart of the atom, and it left no electrical fingerprint at all. The obvious guess was to stuff more protons into the nucleus. But every proton carried positive charge, and adding them threw the electrical books into chaos. A helium nucleus with 4 protons would carry 4 charges, not the 2 that experiments demanded. The mass could be fixed, but only by destroying the charge. Fix the charge, and the mass collapsed. The 2 measurements pulled in opposite directions, and no arrangement of known particles could satisfy both at once. Physicists faced a genuine paradox. The nucleus was heavier than its charge allowed, as if it contained a phantom substance with mass but no electricity. Whatever this material was, it slipped past every detector built to sense charge, because those detectors saw only positive and negative. A neutral thing would move through them like a ghost through a wall. For 3 decades, this missing weight haunted the foundations of physics. The answer would require a new kind of particle, one nobody had ever seen. But before that particle could be imagined, someone first had to find the nucleus itself. In 1911, in a laboratory in Manchester, Ernest Rutherford performed the experiment that carved the modern atom into existence. He fired alpha particles, fast and positively charged, at a sheet of gold foil only a few thousand atoms thick. Most of the alpha particles sailed straight through, as expected. But a tiny fraction did something astonishing. They bounced back, ricocheting almost straight toward the source. Rutherford called it as incredible as firing a shell at tissue paper and watching it rebound. The only explanation was that each atom hid nearly all its mass and all its positive charge in a tiny, dense core. Rutherford named it the nucleus. The atom was mostly empty space, with a concentrated speck at its center thousands of times smaller than the atom itself. This was the birth of the nuclear model, and it reshaped physics overnight. By 1919, Rutherford went further. Bombarding nitrogen gas with alpha particles, he knocked loose positively charged particles that were identical no matter which element he struck. He had isolated the proton, the fundamental unit of positive charge, inside every nucleus. Now physicists had a genuine building block, but the old paradox returned with sharper teeth. If the nucleus held only protons, its charge and its mass could never agree. So scientists proposed a patch. Perhaps the nucleus contained extra protons for the weight, along with electrons packed inside to cancel the surplus charge. A helium nucleus might hold 4 protons and 2 nuclear electrons, giving 4 units of mass but only 2 units of charge. On paper, the trick worked. In reality, it collapsed. Electrons confined to a space that small violated the new laws of quantum mechanics. The energies made no sense. The spins of nuclei measured wrong. An electron trapped in the nucleus should have blurred and broken free, yet the model demanded it stay put. The proton-electron nucleus was a contradiction dressed as a solution, and every careful measurement exposed the seams. Physicists knew something was missing. Rutherford himself began to suspect that the answer was not a combination of known particles, but an entirely new one, silent and unseen, waiting in the dark. In 1920, Ernest Rutherford stood before the Royal Society in London and spoke aloud an idea that sounded like speculation bordering on fantasy. He proposed that the nucleus might contain a new kind of particle, one with roughly the mass of a proton but carrying no electric charge whatsoever, a neutral twin of the proton. He imagined it might form when a proton and an electron fused so tightly they collapsed into a single neutral body. If such a particle existed, the missing weight would finally make sense. A helium nucleus could hold 2 protons and 2 of these neutral particles, delivering 4 units of mass while keeping only 2 units of charge. The arithmetic that had tormented physics for 20 years would suddenly balance. The charge and the weight would agree at last. It was an elegant thought. It was also nearly impossible to test. Every instrument built to detect particles relied on electric charge. A cloud chamber revealed a charged particle by the ionized trail it carved through vapor. A Geiger counter clicked when charge tore electrons from gas. Detectors, in essence, listened for electricity. But a neutral particle would leave no trail, trigger no counter, bend in no magnetic field. It could pass through matter like a ghost, silent and invisible, betraying nothing of its passage. How do you find something designed by nature to be undetectable? Rutherford's proposed particle threatened to remain forever a hypothesis, a convenient fiction that saved the equations but could never be seen. Throughout the 1920s, researchers at his Cavendish Laboratory searched for it, sometimes half-heartedly, sometimes with real effort. James Chadwick, Rutherford's close collaborator, took the idea seriously and hunted for the neutral particle across several failed experiments. Nothing appeared. The particles stayed hidden, and skeptics dismissed the whole notion as wishful thinking. For over a decade, the neutron existed only as a name and a hope. To catch it, someone would need an entirely new approach, a violent nuclear reaction that could knock this ghost loose and force it to reveal itself. That reaction was coming, though the men who first produced it would never understand what they had made. In 1930, at the Physikalische Technische Reichsanstalt in Berlin, 2 German physicists set out on an experiment that would accidentally open the door to the neutron. Walther Bothe and his student Herbert Becker took alpha particles from radioactive polonium and aimed them at a target of beryllium, a light silvery metal. They wanted to see what radiation the bombardment would produce. What emerged startled them. The beryllium gave off a radiation of extraordinary penetrating power, far greater than anything they expected. This new radiation punched through several centimeters of solid lead, a shield that would have stopped ordinary rays cold. Whatever streamed out of the beryllium carried enormous energy and passed through dense matter almost untouched. Bothe and Becker measured it carefully, documenting its remarkable reach. But when they came to explain what it was, they reached for the only neutral radiation they knew. Gamma rays. Gamma rays were high-energy light, chargeless bursts of electromagnetic radiation released in nuclear reactions. They too could penetrate deeply and slip through magnetic fields unbent, because they carried no charge. To Bothe and Becker, the beryllium radiation looked like an unusually powerful gamma ray, and so they labeled it exactly that. It was a reasonable mistake, but it was a mistake. The problem hid in the numbers. To penetrate lead as this radiation did, and to do what it would soon be shown to do, gamma rays would need impossibly large energies, more than the modest alpha bombardment could ever supply. The energy budget did not close. But in 1930, few noticed the discrepancy, and fewer questioned the gamma ray label. The beryllium radiation was cataloged as a curiosity, a strong but explainable emission. The 2 Germans had, in truth, produced streams of Rutherford's ghost particle, the neutron, firing invisibly out of their apparatus and through their lead shields. The neutral particle that had eluded physics for a decade was now being manufactured in a Berlin laboratory, night after night. Yet no one recognized it. The discovery lay hidden inside a wrong name, It would take another laboratory in Paris to push the mystery one step closer and to make an even more revealing error. In Paris, early in 1932, the mysterious beryllium radiation reached the hands of two of the finest experimenters in France. Irene Joliot-Curie, daughter of Marie Curie, and her husband, Frédéric Joliot-Curie, possessed one of the world's strongest polonium sources, giving them intense beams of alpha particles. They repeated the beryllium experiment and studied the penetrating radiation with their formidable skill. Then they added a clever new step. They placed a block of paraffin wax, a substance rich in hydrogen, in the path of the radiation. Hydrogen nuclei are simply protons, and the Joliot-Curies wanted to see what the beryllium rays would do when they struck this hydrogen-loaded material. The result was dramatic. Protons came flying out of the paraffin at tremendous speed, ejected with real force, and detected easily by their charge. The mysterious radiation was knocking protons loose and hurling them forward like billiard balls. It was a striking observation, precisely measured and clearly reported in their published paper. But then, like the Germans before them, the Joliot-Curies stumbled at the moment of interpretation. They still believed the beryllium radiation was gamma rays, and so they concluded that gamma rays were somehow scattering off the protons and driving them out of the wax. On paper, this echoed a known effect, the Compton scattering by which light nudges electrons. But protons are nearly 2,000 times heavier than electrons. For gamma rays to knock a proton forward so violently, they would need a colossal, almost absurd amount of energy, far beyond anything the beryllium reaction could produce. The explanation demanded energies that simply were not there. The Joliot-Curies had performed a beautiful experiment and drawn the wrong conclusion. They held the neutron signature in their data, protons flung out by heavy neutral particles striking them head-on, exactly as one billiard ball strikes another. But they read it as impossible gamma rays and let the discovery slip through their fingers. Across the channel, in Cambridge, a physicist who had hunted the neutral particle for over a decade read their paper. James Chadwick understood at once that something was profoundly wrong, and that the answer might be the ghost he had chased for years. In January 1932, a scientific paper arrived at the Cavendish Laboratory in Cambridge. It came from Paris, authored by Irene and Frédéric Joliot-Curie, and it described a radiation that could knock protons out of paraffin wax. James Chadwick read it at his desk, and by the time he reached the final paragraph, he was already reaching for a different conclusion. The Joliot-Curies had called the radiation gamma rays. Chadwick did not believe it. For 12 years, he had carried Rutherford's 1920 idea in the back of his mind, a neutral particle, roughly the mass of a proton, hiding inside the nucleus. Now, in the French numbers, he thought he could see its fingerprints. Chadwick went to Rutherford that morning and described the results. Rutherford, famously skeptical, listened. Then Chadwick said what he was thinking. This was the neutron. He asked for time and equipment, and he got both. What followed was one of the most concentrated bursts of experimental physics in the 20th century. Chadwick worked, by his own later account, almost without pause. He slept little. He arrived early and left late, sometimes staying past midnight in the darkened laboratory. He assembled his apparatus around a polonium source and a disk of beryllium, the same reaction Bothe and Becker had first struck in 1930. The alpha particles from the polonium hit the beryllium, and the mysterious radiation poured out. Chadwick directed that radiation into an ionization chamber connected to an amplifier and an oscilloscope, so he could count individual recoiling nuclei as electrical pulses. He placed sheets of material in the beam's path, paraffin, but also lithium, beryllium, carbon, nitrogen. He measured how fast the ejected nuclei flew from each target. He recorded velocities, ranges, energies. He was building a case, not with argument, but with measurement. Every reading pointed away from gamma rays and toward something with mass. For roughly 2 weeks, the numbers accumulated on his laboratory notebooks, sharp and unforgiving. Chadwick was no longer guessing. He was preparing to prove it. And to do that, he would have to turn to the two most powerful tools in physics: the conservation of momentum and the conservation of energy. The problem with a neutral particle is that you cannot see it. It leaves no track, triggers no direct spark, bends in no magnetic field. Chadwick could only study it by watching what it hit. So he built his argument on collisions. If the beryllium radiation were gamma rays, pure energy, no mass, then knocking a proton out of paraffin at high speed would require an enormous photon energy. Chadwick measured the protons flying from the wax. They emerged with velocities up to about 30 million meters per second, carrying energies near 5.7 million electron volts. To fling a proton that hard, gamma rays would need something like 55 million electron volts. But the beryllium reaction simply could not produce photons of that energy. The books didn't balance. The gamma ray explanation demanded energy from nowhere, a violation of conservation itself. Chadwick then did what the Joliot-Curies had not. He fired the radiation into different targets and compared the recoils. He measured protons from paraffin and nitrogen nuclei from other materials. Then he treated the collision like billiards. If a moving particle strikes a stationary one, the speeds it imparts to different masses reveal the mass of the projectile. A massless photon could not explain the pattern, but a particle with a mass close to the protons could explain all of it, cleanly, with no missing energy. Chadwick ran the calculation. The mystery particle had a mass almost exactly that of the proton. His figures landed near 1.006 times the proton mass. And it carried no charge, which was precisely why it penetrated so deeply, why it left no ionization trail, why it had fooled Becker, fooled the Joliot-Curies. It slipped through electron clouds untouched because it had nothing for them to grip. The equations of momentum and energy, applied without mercy, admitted only one answer. The radiation from beryllium was not light. It was matter, neutral matter, streaming out of shattered nuclei. Chadwick had measured the invisible by measuring its consequences. The particle Rutherford had imagined in 1920 was real, and now there were numbers to prove it. All that remained was to tell the world. In February 1932, Chadwick sent a short letter to the journal Nature. Its title was cautious: Possible Existence of a Neutron. The tone was modest. The claim was seismic. In barely a page, Chadwick laid out the collision data, the mass estimate, and the conclusion that the beryllium radiation consisted of neutral particles with a mass close to the protons. Within months, he published a longer, fuller paper, The Existence of a Neutron, dropping the word possible. The evidence was now overwhelming. The neutron was real. The scientific world moved fast. What had been a 12-year-old speculation from Rutherford became, almost overnight, the foundation of a new nuclear physics. The contradictions that had plagued the proton-electron model dissolved. There was no longer any need to cram electrons into the nucleus to fix the arithmetic. Instead, the nucleus was built from two particles, positively charged protons and neutral neutrons, bound tightly together. The mass finally added up. A nucleus weighing 4 proton masses, but carrying only 2 units of charge. Helium was simply 2 protons and 2 neutrons. The missing weight had a name and a measurement. In 1935, just 3 years after his letter to Nature, James Chadwick received the Nobel Prize in Physics for the discovery of the neutron. He had solved a puzzle that generations of physicists had circled without cracking, and he had done it by taking one experiment seriously enough to distrust its conclusion. The atomic nucleus, once a source of paradox, now made sense. Every element could be described by its protons and its neutrons. Isotopes, atoms of the same element with different weights, were suddenly obvious. Same protons, different neutron counts. The periodic table gained a hidden dimension. But the neutron did more than tidy the theory. Because it carried no charge, it could slip into the heart of any nucleus without being repelled. It was a key that fit every lock. Physicists across Europe and America immediately began firing neutrons at heavy elements, watching for what would happen when this uncharged intruder struck. They did not yet know it, but they were standing at the doorway to the atomic age. The neutron changed everything, and it changed it quickly. Because it carried no electric charge, the neutron could drift into a nucleus that would have repelled any proton. Within 2 years, in Rome, Enrico Fermi was bombarding element after element with neutrons, creating new radioactive isotopes and pushing toward the heaviest atoms known. In 1938, in Berlin, Otto Hahn and Fritz Strassmann fired neutrons at uranium and found, to their astonishment, the presence of barium, an element roughly half uranium size. Lise Meitner and Otto Frisch explained it. The uranium nucleus had split. They called it fission. A single neutron could break the largest atom in two, releasing energy and, crucially, more neutrons, which could split more atoms in a chain. In just 6 years, Chadwick's modest letter to Nature had led to the discovery of nuclear fission. By 1942, Fermi had built the first controlled chain reaction beneath a stadium in Chicago. By 1945, the same physics had produced the atomic bomb, and soon after, nuclear reactors generating electricity. The neutron had opened a door that could not be closed, a door to power, to weapons, to medicine, to a reshaped century, and it had all begun with a discrepancy in weight. The neutron also completed the map of ordinary matter. Every atom in the universe, from hydrogen to uranium, could now be described by 3 particles: electrons orbiting a nucleus of protons and neutrons. Isotopes made sense. Nuclear stability made sense. The strange arithmetic that had troubled physicists since Rutherford's day resolved into simple counting. The mystery that had opened this story, nuclei heavier than their protons could explain, carrying no extra charge to account for the difference, was finally, precisely answered. For decades, the extra mass had been a ghost in the equations, a weight without a cause, a number that refused to balance. James Chadwick chased it down with polonium, beryllium, an oscilloscope, and the unbending laws of momentum and energy. And when the measurements were done, the answer was as clean as it was profound. The missing weight was a neutral particle,